Hello everyone, welcome to my project presentation on memory management in operating systems using the first fit and then the best fit allocation algorithms. In this simulation, I have designed and implemented a program that dynamically allocates and deallocates memory blocks based on user input. We will explore both algorithms, handle both requests. We will compare their efficiency in terms of time complexity and memory utilization, and analyze the impact of fragmentation on overall system performance. By the end of this video, you understand the strengths and trade-offs of each algorithm, helping to determine which approach works best for different system requirements. Let's dive in, but before I start, I would like to explain some basic terms used. I will start with the first term, allocation. So allocation, to allocate a memory means to reserve space in memory for a program or a process to use. Then deallocation, we say, is the process of freeing up memory that is no longer needed so that it can become available for other processes. And then fragmentation. Fragmentation happens when memory becomes messy or broken into small pieces, making it harder to use and less efficient to use. We would continue by introducing the program's interface. So when the program is launched, the user is first prompted to enter the total memory size. So the total memory size can be referred to maybe the total size of a disk or a memory. So I would enter 100 million, and it will be working in kilobytes, so 100 million kilobytes as we have here. So after the user enters the total available memory, the following options are displayed. Let's quickly run through what each option does. So we have allocate using first fit. So what this does is that it tries to allocate a memory block using the first fit algorithm. And then two, we have the allocate using best fit. So this also tries to allocate a memory block using the best fit algorithm. And then we have deallocate. What this does is that it frees up memory by marking a previous allocated block as free. And then display memory. So this prints the current state of the memory, showing both allocated and free blocks with their sizes. And then the merge free blocks. So this combines adjacent free blocks into a single larger block to reduce external fragmentation. And then we have the simulate fragmentation. So what this does is that it artificially fragments memory to simulate real-world scenarios. And then we have the reset total memory. So what this does is that it clears the entire memory and resets it to the original state with one big free block. And then the fragmentation to initial state. So what this does is that it restores the memory state to initial fragmented state. So for example, if we have simulated fragmentations and then we have used that for maybe best fit, we can reset the same fragmentations to use that same sizes for the first fit algorithm, and then the exit quits the application. I will demonstrate how each algorithm allocates memory to a process. Before we try to use any of these algorithms, I would explain what they are. I will start with the first fit algorithm. The first fit algorithm allocates memory by scanning the whole memory from start, and it allocates the first free block big enough to fit the requested memory size. If the block is larger than needed, it splits the block and leaves the leftover space as a free block. For instance, I want to allocate 700 kilobytes of memory for a process. The first fit starts to scan the memory for a free block which is big enough to fit 700 kilobytes. As soon as it finds the first free block enough to fit the 700 kilobytes, it stops there and then allocates the 700 kilobytes to that free space it has found. Let's look at the best fit algorithm. So the best fit algorithm scans the entire memory and allocates the smallest available block that can accommodate the requested size. By choosing the smallest possible block, the best fit aims to leave larger free blocks available for future allocations, making it a more space efficient strategy. So for instance, I want to allocate the same 700 kilobytes of memory for a process using best fit. The best fit scans the entire memory from start to the end to find free blocks which are big enough to fit 700 kilobytes. When this scan is over and it has found free blocks large enough for the 700 kilobytes to fit, the algorithm then picks the least amongst these free blocks to allocate the 700 kilobytes requested. So from this we can say that the first fit allocates the requested memory immediately it finds a block large enough to accommodate the requested memory, whilst the best fit scans the entire memory, finds free blocks, and then chooses the least among these free blocks to allocate the requested memory to. So now I will demonstrate practically how each algorithm allocates memory. But before we start, let's display our memory using option 4 to see the state of our memory. So option 4, enter. So then it says memory state. We have a free block of 100 million kilobytes. Okay, so before we use or allocate using any of the algorithms, we will first have to simulate fragmentation so that as we allocate, the allocations can simulate or resample real life scenarios. So I will choose the option 6, which will simulate fragmentations. So option 6, enter. So it says simulated 1000 random allocations with random deallocations. So you can display the memory option by using the memory option to view them. So free blocks. So I have simulated 1000 random allocations with random deallocations. So now let's display our memory again. So yes, then we see the simulation worked. So now we have 1000 blocks. Sorry, 1001, including our main block plus the 1000 simulated fragmentations. So then let's try allocating the first memory using the first fit. So we'll choose the first fit, which is option 1. So it says enter the memory size to allocate. So let's go through and then try to find a memory which is in common so that we can use that to allocate. So I will try 700. Yes, I will try 700. I will try to allocate 700 of memory using the first fit. So I want to do this 5 times so that we can gather some data and see how the first fit allocation works. So 700 kilobytes. So it says we allocated 700 kilobytes using first fit in this time with 5 comparisons. What the comparison means is that it starts scanning from the first block. So this is empty, but it cannot accommodate 700. This was filled up. It cannot accommodate 700. So this is the third comparison, cannot accommodate. This is the fourth, cannot accommodate. So the fifth was able to accommodate the 700. So that's what the 5 comparison means. So let's try that again. Option 1, we allocate 700. So it says we are able to allocate using the first fit. with 12 comparisons. The comparison means it compares the blocks, how many blocks. So the first 12 blocks. So what it means is that I was able to find a free block which is large enough to fit or accommodate the 700 kilobytes after 12 comparisons. So we'll try that again. Option 1, 700. Yeah, so as we move on, we see the comparisons are increasing. We'll try that again. Option 1, 700. 21 comparisons. Let's see if 1, 2, 3, 4, 5. So we've tried 5 times. Let's display the memory and see. So using option 4, display memory. So we'll start. So this was the first, second, third, fourth, fifth. So we saw a fifth comparison here. Yes, so 5 comparisons. So it found a block available to accommodate 700. So which block was that? The fifth block was 972. So this is how the first fit works. So when it finds the first block enough to accommodate the requested memory, it allocates or it splits the memory like it has done here. So it splits the memory into 2. So 700 and then the remainder 272. So it splits the memory into 2. 700 occupies one side and then leaves the remaining, which is 272 kilobytes as a free memory. And then the next one, we have 12 comparisons. So we started with this. Nope, this wasn't suitable. This, up to the 12th one. So this is the 12th one. So before in our memory, the 12th one was 814, which was free and then can accommodate the 700 kilobytes of memory requested. So what did he do? It's allocated 700 of the 814 to that and then left the rest over. So this is how the best fit works. So as we continue, you will see that as it finds the large block enough to fit the 700, it accommodates it and then leaves the remaining. So now we have a clear understanding of what the first fit, how it allocates blocks. So when it scans, it starts to scan the memory. When it finds the first memory available and then big enough to accommodate the requested memory, it allocates the memory there, and then if there are leftovers, it leaves it as a free space. So now we'll continue with the best fit algorithm. We'll look at how the best fit also works. So before we do that, I want to use the same fragmentation we use for the first fit. So I have an option here to reset fragmentation to initial state. So 8. I'm using the same. I want to use the same because I want a consistent date. I want to be equal to both. The same fragmentation for best fit, the same fragmentation for first fit. So reset fragmentation to initial state. It is fragmentation reset to initial state. Let's see if it worked. So let's display memory. Okay, so let's see. There's the memory. So we don't see the 700 allocated here no more. We don't see it here no more. We don't see it here no more, like they were in this. So let's try and allocate using the best fit and then see how the best fit works. So best fit will allocate the same 700. So we see here, it says what's allocated 700 using 700 kilobytes using the best fit in this seconds with 1001 comparisons. What this 1001 comparison means is that we have 1001 blocks here. So it searched through the whole 1001 blocks. It found free spaces that can accommodate the 700 kilobytes, and then use the least space amongst these free spaces it found. So we'll try that again for 5 times. So 2 option 2 700 kilobytes. So we allocated this, yes, using, so now our comparisons are increasing. What it means is that the first space it found, it left a leftover. So the leftover space has been added to the blocks. So now we have 1002 blocks. We'll try that again. 700. As we keep doing this, we realize that the blocks keep increasing. Fragmentation keeps increasing as we do this. So we'll try that again. 700. Yes. Try that again. 700. Yes. So now we can display the memory and then see how our memory looks like now. So here we can see, even though it's allocated, so we can see that the best fit didn't allocate the 700 to the first free block that could accommodate 700, even though it could accommodate. So let's quickly do something here. I would copy these blocks and then copy the first fit blocks also, and then we'll do something quickly here. So I have copied the memory status after 5 allocations using the first fit. Let's try and then find all the 700s we were able to allocate. So we were able to allocate 700 5 times. And then we see that the 700 are just at the top of the memory. That's the first 700, the first blocks, the first fit was able to find that code accommodate 700. First 3 blocks. So we have this here, this here, this here, this here. So the first 3 block, it doesn't care the number or the size it leaves behind after allocation. So with this, it left 272 kilobytes of free block behind. With this, it left 41 kilobytes of free block. With this, it left 114 kilobytes, and this, it left 283 kilobytes of free block behind. Now let's do same for the best fit. So I will go on and then copy for the best fit. So this is for the best fit. I would copy this. Then here we will see the difference. We will see the real difference between the two. So I will paste this here. And then we will search for 700. Yes. So we see for the best fit, it didn't start allocating when it found the available block, the first available block, but rather it scanned through the whole blocks, and then we see the ones highlighted in yellow. We see there are very small blocks left over. So the best fit tries to find the best suitable block for the requested memory. So this we see we have 6 kilobytes, 6 kilobytes, 2 kilobytes, 12 kilobytes, and then we have another 12 kilobytes. So we realize that the best fit tries to minimize wastage of space by allocating or finding the best blocks, the best least blocks that can allocate the requested memory without leaving larger spaces behind, unlike the first fit. So we'll go on to look at their advantages and disadvantages. So let's look at the advantages and then disadvantages of the best fit, the first fit algorithm. So the advantages of the first fit, we realize that the allocations were fast. Let's see if that was true. So here we have, let me see. So the the 100 and fit comparison, we have just 3 zeros after the dots. Let's see this. For the first fit, you see we have 4 zeros, which means that the first fit is faster in allocating memory than the best fit. So we see all these are 4 zeros after the decimal point, whereas even the best fit could go up to just 1 0. This 0 might depend on maybe the system. We can see that this is a clear evidence that the first fit is faster in allocating memory than the best fit. And then another advantage is that when it comes to the time complexity, it uses a big O of n. So it uses a linear time complexity, which is big O of n, where n is the number of blocks it has to scan. And then another advantage of the first fit is that it is simple to implement. So it requires just a sequential scan of memory. And then another advantage is that it uses fewer comparisons compared to the best fit. And then another is minimal processing requirements, which makes it ideal for systems where speed is more critical than memory optimization. So we look at the disadvantages of the first fit algorithm. So one is the first fit algorithm leaves small unused memory blocks, which may be large enough for future allocations. So in the first fit, we saw that it was leaving 272, was leaving blocks which could sum up to accommodate a future process. But since it's leaving them, so I assuming it has left 272, and then maybe I want to allocate, maybe in future I want to allocate a memory of 300 kilobytes to a process. That wouldn't fit because 272 is lesser, and then in this the memory has been wasted. The memory has been wasted. 272 wouldn't fit the required 300 kilobytes we are asking for. And then with this, another disadvantage is that the fragmentation increases over time. And then we might overlook better fitting small blocks instead of splitting larger blocks unnecessarily, leading to inefficient memory use. I'll take this again. So the first fit might overlook better fitting smaller blocks and instead split larger blocks unnecessarily, which will lead to inefficient memory use. And another disadvantage is that although it stops at the first suitable block, as memory fills up, it may still need to scan a large significant portion of memory, especially if large allocation fails early. And then let's move on to systems suitable for best fit. Systems or suitable systems for best fit. So it says one, where speed is needed or where speed is crucial. So an example of a system where speed is crucial is we have the IoT devices, embedded system, or simple task schedulers. And then Another suitable system for the first fit is a system where environment fragmentation can be periodically resolved through memory defragmentation. So examples of these environments where fragmentation can be periodically resolved are batch processing systems where memory is cleared between jobs. And now let's look at the advantages of the best fit algorithm. So one, we say an advantage is that it minimizes leftover memories by allocating the most suitable blocks. Two, it helps conserve memory by preserving unnecessary large blocks from being split. Three, it is more efficient, a more efficient use of memory as large blocks are preserved for bigger requests. Now we'll move on to suitable systems for best fit algorithms. So we didn't look at the disadvantages. So the disadvantages of the best fit algorithms. So one, it requires scanning the entire memory to find the smallest possible fit. That's a disadvantage. So a worst case time complexity of big O of n, which can be slower than first fit, especially in fragmented memory, as we showed in the difference in times between the first fit and then the best fit allocations. So although it minimizes leftover space for each allocation, it may create tiny unusable fragments over time. These small fragments accumulate, increasing the likelihood of unusable fragments over time. These small fragments accumulate, increasing the likelihood of failed allocations despite having enough total memory spaces. So allocation time can be very drastically depending on the memory state. So with the best fit, if your memory is heavily fragmented, the best fit will use more time or find it more difficult to allocate memory since it has to scan your heavily fragmented memory before allocating the memory to it. So then we'll look at systems where best fit algorithms is best suited. So one, we say the best fit algorithm is ideal for systems where memory is scarce and efficiency is more critical than speed. So examples of these systems are low memory embedded systems, firmware or resource limited devices. And then the second system where best fit algorithm is suited are systems that stay operational for long periods and can tolerate slower allocations in exchange for better long-term memory optimization. So examples of these systems are servers, databases, and virtual memory managers.